along with all of you. So we will not be doing any other mode of taking an attendance. Once you have filled this Google form, as the discussion goes on, responding to various questions, that is what would ensure the attendance part. So because we have certain formalities that we have to comply with as per strict requirements from ATAL agency. So now we wanted to make it as an opportunity to have an interactive session. So there would be questions which will be asked along the session, and you can look into the Google form and fill in your details. These are very preliminary question, very like simple questions to look at, but very deep as we discuss them further. Okay, so at the end of the session, when we together discuss some of the key issues, you will find that these questions are really pointers to internationally competitive research that we can possibly do or pursue or we can plan. So, so that is one point. The other thing is you can also see this QA toolbar. If you see my cursor, you can see this Q/A bar. So at any point during the talk, you can just tap on it and fill in your question. So what we can do is at the end of the session, we can go to this Q&A bar and we will look at what all questions were there, because while the speaker is actually addressing the entire gathering in online mode, it's not always possible to look at the questions on the go. So this Q&A bar allows these questions to be kind of formed into a repository which can be looked at immediately after the talk. And if there are questions which require further detailed inquiry, like the speaker will get back to you later, right? So these questions need to be there. So I hope both the things are clear to you. There's also this like raise hand bar. So if it is both the things are clear to you, you can simply tap on it. So for example, I can say I can raise my hand if I have a question, but otherwise I can simply like. So if I like, that means that I have understood whatever is being asked. So along the session, we may also ask you to use this reaction bar, or the speakers may actually look at the reactions on the go. Fine, if these things are clear, we will proceed. So for a moment, it would be useful if everyone switches on their camera so that we understand that we are speaking to real people. And then once we start the session, everyone can switch off their cameras. So I request that for about half a minute, if everyone can switch on their cameras. Yeah, more people. I think I can make it a larger gallery. Yeah, so I've already made that into a larger gallery here. So are people having reservations in switching on their cameras? Because this is supposed to be an interactive session, so we would like to, like, it's a mutual courtesy if we see you. Fine, so I think like today is a chutti, so people may be at different places, so we don't want to. So we will go ahead with the session now. Thank you so much. Maybe you can switch off your camera and I will do the same.
Okay, sir.
Please let me know if the title screen is visible, and then we can start.
Yes, yes, sir. Yes, sir. Visible.
A very good afternoon to everyone. So let's start with the first session of this ATAL FDP on novel materials for sustainable development. I am Ajay Thakur, I'm an associate professor at IIT Patna, and today's session I have planned just to make sure that we sensitize ourselves about the role of materials in sustainable development. So why novel materials? Like, why do we call them novel materials? And what is this idea of sustainable development and why these two things are interrelated? So like it's an well-known fact that materials are indispensable for technological developments, and you can see that material goes into almost everything, be it structural materials, like we are living in houses, we in the comfort of houses, and in making these houses we have used structural materials. We use energy. So as we use, say, electricity in any form or heat in any form. So materials are involved in the process, right? When we are using any gadgets, various types of electronics, there are various types of materials which go into making them. Like while we are unwell, we use medicines of different kinds, and they are also made out of different types of materials. And besides that, like nowadays, the way our indiscriminate use of materials have caused issues to environment, there are material interventions to actually take remedial action. So therefore, even there materials are useful and more. So accordingly, across this workshop, we will have speakers from various institutions who will talk about various aspects of materials which are relevant to different types of applications, like be it related to electronics, be it related to energy, like green energy, be it related to other domains. So materials therefore are making everything, and what we see is like even things like clean energy, clean water, like they also today are asking for a variety of material inputs. So we cannot think about having clean water until and unless we are using materials in certain formats. So say for purification, there are specialized membranes that we use. Say for clean energy, like when we say clean energy, it means there is a very little impact on environment because of the mode of having that energy. So even that will require different types of materials, and there are so many other things, one of the latest being IoT. So when we say Internet of Things or whatever we are going into, like we will have smart surroundings, smart homes. So there would be lots of devices connected with each other, talking to each other, interacting with each other to monitor various aspects of like day-to-day activities, right? So that will involve IoT devices, and even IoT devices require variety of materials. So therefore, it is very, very important from the perspective of sustainability to put constraints on choice of materials. So the materials in general have to be non-toxic for most applications. They should be available in Earth's crust in enough abundance. So if there are applications which require us to use bulk quantities of materials, uh, right, with which goes into production line in a massive way, then these material ingredients cannot be rare earth materials or cannot be materials which are really rare within Earth's crust. Besides that, there has to be cost effectiveness in the processing strategy, and any of these material systems that we think about for applications, like the overall preparation strategy and conversion into devices, that should obey some kind of a scalable approach because without that, large scale implementation of the discoveries is not possible. So therefore, what has been realized is whenever we invent or introduce a new material, we are actually enabling new technologies and society changes. So the best example is our own evolution from Stone Age to Bronze Age to Iron Age to Silicon Age. And you can see that each is marked by specific materials. And when I put these three dots at the end of Silicon Age, we are really looking forward to future. Like we are already seeing nanomaterials making an entry into variety of applications. We are seeing within nanomaterials, in particular, 2D materials are playing important role. Quantum dots are playing important role, be it medicine, be it day-to-day like applications. So nobody can really deny the utility of materials. So what I would ask you is go to the Google form and answer the first question over there. So there are one or two or three very common questions where you have to simply put your name, email, and maybe some detail related to your attending the offline session. After that, there is a first question related to utility of materials. So I would expect all of you to spend maybe 30 seconds and quickly jot down your, or basically tap down your entries into the Google form with respect to that question. And when everyone is done, you may use this reactions button to raise your hand so that we know that everyone has done it. See, in the screen, you can see different people. Say, for example, if I simply raise my hand here, that means I have kind of done this question. So I expect others to fill that in within the Google form. Google form is already there within the chat of this, the link to Google form. I will put it again for those who have joined late. Once you are done, please raise your hands because there's no other way of keeping this entire session interactive. Yes, so maybe roughly half a minute is over. I'm not seeing much reactions here in the toolbar. See, as teachers, all of us like to interact within classrooms. So unfortunately, this online mode has its own limitations, but it also has lots of nuances which help us create a feel similar to a classroom. So if everyone is done with it, please raise your hand with a reaction. Dr. Pradhan, Dr. Karuna, yeah. Fine, I can see some of them have already filled in. So uh, what we will see later is we'll actually go through these suggestions that people have put into various questions, and that would be a good ground to initiate the discussions. Fine, so in the spirit of time, I will go back to the presentation. Yeah. So let me just hide this toolbar in case. that will help us. Yeah. So therefore, like what we eventually see is there is a important synergy of basic sciences and technology that is going to have tremendous implication on how we choose materials. And over next 2 to 3 slides, we will realize how in last 150 years, we have been doing an indiscriminate usage of materials, which has really already started causing issues. So we have lived through this era of plenty. So when I say era of plenty, we are talking about this philosophy or the business model of take, make, use, and dispose. So over here, the prime activity has been focused around locating specific material. So suppose if we require indium for a particular application, so there would be efforts at locating where indium mines are located. The second was mining it. The third is refining it and then using it. So in this entire process, like there has been an era of increasing affordability. So different systems have become more and more affordable. They are being consumed more. Right. So even if we say indium goes into making displays, so now we see we have displays all around, displays inside our pockets in the form of smartphones, displays in our inside our vehicles. So even while we are moving from one place to another, we can have access to displays. So over last 10 years, these have really exponentially risen. So that is the second point of consumption. And the third point is associated economic growth. But at the same time, there have been very little control on the way materials were used. So most importantly, the end of product life is not really planned very well. So that has really led to a realization of key issues related to environmental impact and total cost. And these are associated with this idea of sustainability. So like over here, you have a next question, like in your views, can you see examples where indiscriminate use of materials have led to issues? So you can jot down or tab down 2 or 3 such examples in the Google form, and then we'll proceed. So in the Google form, there is a next question which talks about examples of indiscriminate usage of materials. Okay, fine. So we will also give you some time at the end of the talk to kind of finalize your answers and then submit it. So we'll proceed. So here I would like to draw your attention to certain thoughts. Like first of all of us know that global population has already exceeded 7 billion and it is ever increasing. So accordingly, demands are rising. So demands for, say now handheld devices, for example, like, so we are here not even talking about very basic necessities like food, water, and clothing. So their demands are also rising, and there is also materials involved there. Say, for example, when we are talking of food, so food productivity is associated with usage of fertilizers. So how much of fertilizer can we use? Water, like so water treatment. So the process of treating water itself involves a lot of materials. So how we are really addressing them. So these demands are ever increasing, and there are already clear evidence for the limited capacity of the ecosystem to cope up. So there are many participants from, for example, Chennai, and we already know that there is a severe water crisis going on around. Not only Chennai, there are many other parts of the country and the world which are facing similar issues because of lowering water tables. So air pollution in cities, water pollution in rivers, chemical contamination of land. So all this have really kind of started showing up their faces, right? Besides that, uh, now products are becoming more and more complex. So maybe 50 years ago, if you compare certain products with certain products that we use today, or the new types of products that we are using today, they are far more complex, and therefore there is a dependence on large number of elements. And when I say elements, I'm actually talking about the elements in the periodic table, and some of these are comparatively rare. So manufacturing nations are competing for exclusive rights over these materials, and new and expanding legislations for manufacturer responsibility are also therefore being put in place. So sustainable development therefore requires thriving in this changing environment. So why we are discussing this? Because we would like to emphasize this point of novel materials in the context of sustainable development. So now there is this next question, which is really talking about what is sustainable development. So those who would like to answer, they can answer, or we can also answer towards the end. There may be people who are actually using two different devices to do it, so they can possibly do it. Otherwise, you can do it towards the end of this session. So that's the next question, which is really asking about sustainable development. And we all know that use of energy, water, and materials is indispensable. Like if tomorrow somebody asks us to go back to caves, that's not possible, right? We indeed want to thrive in the environment or in the ways of living that we have um, got set into, because there are many advantages of doing so. However, uh, like how do we really continue to meet the needs of today without really compromising the ability of future generations to satisfy their own needs or meet their own needs? Like that is what we can define as sustainable development. Okay, so there can be many examples to do this. Say, for example, if we are only depending on fossil fuels today, so these fossil fuels have their own finite availability. So in all likelihood, in next 50 years, 4 to 5 decades, we would have already used up all the fossil fuels, or a majority of it, and then it would be a rare commodity. And today we see even electricity that we use in some ways connected to fossil fuels in a major way. So these thermal power plants are using fossil fuels. So therefore, this sustainable development idea is crucial, and the methods that we choose to achieve these sustainable development goals must be equitable and as per the rule of the law. So therefore, it is desirable to have a thoughtful, well-researched response that recognizes the conflicting priorities of environmental, economic, legal, and social aspects of a technological change. So I'm providing a typical list of new technologies that we are seeing already. So there is IoT, smart cities, robotics, drone, AI, machine learning, blockchain, genomics, nanotechnology. So all of these are excessively energy intensive. So there is huge demand of energy. So within our own local perspective, India is on a tremendous growth trajectory, and we need to watch our own carbon footprint. We cannot go the same way as the West went from developing to developed nation. And simple things like clean water and food security for 1.4 billion citizens of our own country is a big issue, right? So here, let me just try to kind of demonstrate the magnitude of the problem that we are kind of upfront with. So on the left, let's focus on the left hand side, right? And let us try to look at the number which is written over here. It is saying 18 terawatt year. So how do we look at terawatt year? So all of us are aware of this unit of electricity called kilowatt hour, right? So a terawatt hour would be something which is 10 to the power 9 kilowatt hour. A kilowatt hour is 1000 watt hour. A terawatt hour is 10 to the power 12 watt hour. So therefore, 18 terawatt year would be something which would be a 18 terawatt hour usage across the entire year. So if you kind of say if we have a 2 kilowatt hour unit of air conditioner, and if we run it for the entire year, the energy consumption for that would be 2 kilowatt year. So similarly, now we can make a sense of 18 terawatt year. This was the world annual energy consumption in 2015, and this has already crossed 24 terawatt year currently. So now let us compare that 24 terawatt year with available resources that we have around. So say natural gas that we have, that is about 215 terawatt year. So if we are only talking about natural gas as the source of energy, and if we have 25 terawatt year of annual demand worldwide, so these natural gas alone will not even survive a decade. When we talk of oil, again, oil reserves, the known oil reserves are not going to last beyond 240 terawatt year. So if there is a 25 terawatt year demand annually, so it's not even again crossing a decade. Uranium, depending on like the claimed versus actual availability, ranges around 90 to 300 terawatt year, because there are various reasons why certain countries will not declare their exact uranium availability, right? So that again you can say it would hardly last another 10 years, and then we have about 900 terawatt year of coal. So this is a huge compared to other sources, a huge resource, but then at current usage rate, we are not even going to last more than 3 decades, 3.5 decades. So all this taken together is not going to serve us beyond 50 years, right? There would already be energy crisis by that time. So that is something which we have to be really aware of. While we are doing this, while we are looking at these numbers, we have to understand that at a typical illumination of 1 kilowatt per meter square and the typical hours of sunlight availability, solar alone has a capacity of, like sun alone, I would not say solar because that's kind of misrepresentation here. Sun alone would be capable of providing 23,000 terawatt year of power. So therefore, looking up to sun is the only best route forward, right? So how do we really tap energy from sunlight? We have already seen that photovoltaic panels have started finding popularity because there is a grid parity which has been achieved depending on the production cost of solar panels, and the cost of installation of course is very high. However, um, like over few decades that can be recovered, and therefore in some way solar photovoltaic devices are appearing to be solving part of the problem. But then, as we discussed about the total cost of any particular product, right? So even these photovoltaic panels, they have their associated total cost because they have a finite lifetime of usage. So after maybe say 2.5 decades, you will have to replace these panels and you will have to dispose this. So this waste coming out of solar photovoltaic devices, that is seeing or that is kind of standing in front of humanity. We have to face that. In addition, in order to use energy generated in photovoltaic during night time, we also have to depend on batteries. And the current state of the art battery technology has its own associated cost to environment. So like the production of batteries, the chemical processes which are involved there, the running of batteries to the disposal of batteries. Those are throwing important and interesting challenges. So other ways of using sunlight is important, and we will see that at least two of our speakers are going to introduce to you different interesting researches which are ongoing, where they are trying to tap sunlight to convert it into a usable form of energy, right? So that is something which we'll go through in this workshop. So now if we are only talking about photovoltaic cells, and suppose tomorrow we develop technologies to make photovoltaic cells which have a much smaller environmental impact and a much smaller total cost. So then a modest 10% efficiency solar cell will require only about 0.01% of Earth's land area. So this is equivalent to say a 1% area of Sahara Desert, because this is the talk given from physics perspective. So physicists like this Fermi problems. So here one of the interesting Fermi problems is how much area of Earth crust like that we need to really fill to meet the energy demands of say 25 terawatt year. So it turns out only 1% area of Sahara Desert is enough. And just to put things in perspective, like India consumed about 908, say M is say mega, right? 10 to the power 6 tons of oil equivalent in 2020. And this can be converted into units of terawatt hour. So that turns out to be a little over 10,000 terawatt hour. And that translates to about 1.2 terawatt year. So one can see that we are also an important consumer of energy, right? So if we are saying world is consuming about 25 terawatt year, we already have a significant share, about 5% share of this entire thing. And this is only going to increase because we have seen in last decade how mobile phones have become, or certain gadgets have become household items. In a similar manner, Internet of Things, like getting into our households in a massive way, would further increase the demand for energy. So internationally, and therefore this 25 terawatt year of world consumption, power consumption, is only going to increase gradually. So therefore we need to parallelly invest in developing uh, newer technologies, and for them new novel materials have to be planned, limiting ourselves to the restrictions that we talked about related to non-toxic nature, abundance in earth crust, convenient processing, scalable approaches, and so on, right? So now let me just point to another area, and that is related to this global drinking water challenges. So drinking water scarcity is a global challenge, and within India also we are facing it. So as per WHO reports, about 2.2 billion people have limited access to clean drinking water, and 600 million people are facing acute water shortage within our own country. There is bacterial and chemical contaminations. About 2 billion people use water which is severely contaminated, like internationally. And 70% of Indian households drink unsafe water. So these are all as per like various reports. So in India alone, about 22 million people are suffering from one or other form of water contaminated disease. So that is about 2.2 crore, say 220 lakhs, right? So bacterial and chemical contaminations pose severe challenges besides that, and so on. So therefore, safe drinking water is a important index of how developed a country is. And this is how kind of it has become a big challenge, right? So that kind of asks for your views on how one can possibly address drinking water challenges. So you would have seen that till now we have not really talked about any individual materials. So that is not the goal of the first talk. The goal of the first talk today is to sensitize all of us about the challenges that the world is facing today, which requires our approach for novel materials from a sustainable development perspective, right? So being aware of these questions is very, very important, right? So here, like I would now come to a case study, and this is depending on some of the research work that we have been carrying out in our own group, and that is related to the potential of moisture contained in the atmosphere itself. So atmospheric moisture is a really untapped renewable source of fresh water. So there is about 14,000 billion liters. So if you say the world population, like we talked about the world population, right? So each person has his own share or her own share of atmospheric moisture. However, all of us know that if we have to kind of condense moisture from atmosphere, right, it is going to be a highly energy intensive process, right? So therefore, it is important to look forward to technologies which can do it in a less energy intensive way. So here, nature can provide us a lot of insight. Say in the center, like over here, you can see the central figure. So you can see a spider web, and you can see a lot of moisture which has condensed on the spider web, right? Besides that, like there's this Namibian desert beetle. So Namibian deserts, they have a huge water scarcity, and still the life forms over there have survived over ages, and they have developed their own technologies, so their own evolution processes. So these Namibian desert beetle, they have very interesting nanostructures on top of their skin, leading to pores in their skin. So what really happens is water condenses on the skin, and then like it trickles down into these pores and collected inside the body. And that's how the water needs are satisfied. In a similar manner, this Australian green tree frog has also evolved its own ways of capturing water. So inspired by these techniques, human beings have over the years uh, like developed technologies for fog harvesting, for dew harvesting, and um, like leading to this overall gamut of technologies known as atmospheric water harvesting. And like in the left, you can see the atmospheric water harvesting related publications in Scopus search engine journals. And you can see that by 2020, there have been about 1,000. You can compare this number with other areas in technology. Like there are millions of papers published every year. right? If not millions, a fraction of a million. And here, even in 2020, about only 1,000 papers were there. So this is a very interesting and upcoming field, upcoming research area. So there are key challenges here. So large collector areas are required because condensation is a process which is directly like the amount of water collected or the yield is directly proportional to the overall area. So large collector areas applicable to only particular geographical locations. So there are certain geographical locations where this moisture can be condensed only for maybe a very small portion of the daytime. So the early morning time. There are very few regions where this moisture could be condensed all across the day. Right. The water yields are small, and then there are issues with toxicity and low cyclic stability because of um, like the available like pollutants within the air. So they are also, because this is a process which requires a lot of time. So within that amount of time, a lot of dust particles and other pollutants also kind of are collected. So a separation of this is a big challenge. So um, like refrigeration based atmospheric water harvesting is one of the way forward. However, this is really energy intensive. So here is a water harvester which is really working on the principle like where there is a compressor based cooling mechanism, and then the moisture from the environment, from the atmosphere, that condenses on these grids and they are collected. So there is a product, by the way, which is based on this technology, like developed by IIT Madras, like which is easy to operate and compact, but then it has its own challenges, right? It has its own issues. So, and globally, like there have been different efforts at trying to address this problem. So over here, one of the big challenges had been the the limitation on the surfaces. So if you see, let me just go back to this. So if we are using an ordinary metallic plate to condense moisture, as soon as a thin layer of moisture is condensed on the surface, there is a insulating layer which is formed on top of the metallic surface, and it is no more available for further condensation. So as soon as moisture is condensed, it has to be removed, and that is a almost impossible task as it appears. So that is where this inspiration from Namibian desert beetle is useful, or say the lotus effect is useful. So you can see that as soon as water condenses, so these are time lapse videos. So it is really happening over much longer time scale. But then if we speed up the video, you can see that like water condenses and it really collects at the center. In a similar manner, you can see in the other examples over here, like at the bottom, and there are specific papers which you can refer to read further about these. So like, can we really mimic nature and make super hydrophobic surfaces which are having dropwise condensation allowed? So basically what really we need is you can have a surface with a microstructure on top of it, or rather a nanostructure on top of it, so that moisture, as soon as it is condensed, there is a contact angle related issue which forces it to kind of trickle down. So we will know more about it as we progress further into this talk. So there have been a lot of efforts in last 2.5 decades in this area. However, the biggest challenge has been most of these super hydrophobic surfaces uses a coating on top of it, which is not very good. So all of you would have heard about chlorofluorocarbons, right? So they were once used as a gas within refrigerators for refrigeration purposes, and later on we arrived at the conclusion that they are really leading to, these chlorofluorocarbons are leading to ozone holes. So in a similar manner, most of these coatings for superhydrophobic coatings, they require PFC materials. So perfluoro compounds, perfluorinated or perchlorinated compounds. So these PFCs are really not good. So an alternative method is therefore required. So that is where, like I'm going to show an example now from some of our work here. So let me just come to that. Before that, like literally these were the past methods of making these superhydrophobic surfaces, and most of them will have a final stage or final step where these PFC compounds are used, and therefore they really like the use of PFC materials is really not recommended. So what we came up with is a electrodeposition strategy to make nanostructured surfaces on top of copper. And then we came up with a strategy to functionalize the top surface with lauric acid. So lauric acid is something which is available in, say, fruit extracts or fruit skins. So if we are talking about, say, apple or certain other fruits, so there would be uh, the skin of these fruits from which lauric acid could be derived. So this completely leads to potable water. So here you can see how a surface which is made using our technique, like that leads to droplet rebounding effect. So as soon as like a droplet is impinged on top of it, you can see that it's very nice hydrophobicity. So as soon as condensation nucleates and a mini droplet is formed, if you keep the surface at a small angle, the water droplet will trickle down and will be collected. So that is what is the technological intervention here. So we can say that a mundane material like copper was converted into a novel material using the strategy like just explained. So so this is where I would like to bring your attention to this idea that novel material does not always mean that it will have very exotic elements put in very strange concoctions, right? Even the strategies used for making the materials, by tweaking them, if we can introduce interesting functionalities from our application perspective, like that would itself convert it into a novel material. The other point which I wanted to discuss beyond this challenge of water is the food waste. So food waste is a global challenge. In fact, 1/3 of the food produced is wasted around the globe. So these losses amount to around just about $1 trillion annually. So like 1/4 of global food wastage can feed about 870 million hungry people. So like these are some statistics which really kind of pushes us to think that how we can avoid these food wastage. So what could be one of the reasons for food wastage? As we have already been halfway around the talk, I would urge some of you to unmute and tell me like what could be the main reasons why food is wasted. So would somebody like to address this? Like why is food really wasted? If we say 1/3 of food produced is wasted, what are different modes of food wastage?
Uh,
Yeah.
in the earliest stage of harvesting, improper storage of food materials.
Okay, thank you. Thank you. So, can you introduce yourself? Can you tell your name?
I'm Dr. R. Srinivasan from Dundigal, Tamil Nadu.
Yeah. Okay. Thank you. Thank you, Dr. Srinivasan. Anybody else would like to add something? Yeah, please.
Sir, good evening. Myself, Dr. Varaprasad from Visakhapatnam, Andhra Pradesh.
Right.
The main wastage of the food is they are having more than what they can eat in the plate, first one. And second one, while planning an event or a function or organizing anything, they are cooking more than what they actually called for. So especially like marriages, there is a lot of food wastage, and we can see regularly in our canteens also, nearby canteens also, we can see a lot of food wastage because they are not doing as per the plan. That's my opinion, sir.
Thank you. Thank you. Thank you. Any more opinions? So we have already come across. Yes, yes, please go ahead.
Yeah, good afternoon. This is Dr. R. Parani from Tamil Nadu. See, mostly the food waste is wasted in the places where mass gathering actually. See, if you see the marriage all and all, they serve the food before the people come and sit. So some people they like that dishes and they some they don't know. So in that places most of the food is wasted. So instead of that, if they serve once the people are sitting, that can be minimized. That's my point.
Okay, okay, okay. Thank you. So somewhat similar to what Dr. Varaprasad conveyed. Yeah. So we have seen like Dr. Srinivasan and Dr. Varaprasad and the previous speaker, like, so all of them have conveyed their own ideas, and they really fall into two classes. One is this lack of technological intervention. So number one, and the other one is a social issue or a socio-cultural issue. So both of them are really contributing to this big issue. And it turns out like the first one has a lion's share in this wastage cycle. So our inability to provide suitable cold storage chains like that really or like food processing facilities that really causes a huge wastage, because a lot of the grains are rotting before they can actually reach the consumer. The fruits or vegetables, they have limited shelf life. So if they are not stored properly, even the limited shelf life is not used conveniently. And then there are these dairy products like milk and other things. They are also having very small like shelf life. So accordingly, they are also a major fraction of that is also kind of wasted. Dairy product, including milk and meat, like both have their own issues arising due to lack of cold storage facilities. So that is what we would also explore. So we can see in our local context, India is second larger producer of fruits and vegetables in the world. However, we are on the 102nd position, maybe plus or minus few, like after 2019 when this report was published. But that is our typical standing in 117 countries in global hunger index. And 18% of vegetables and fruits are wasted every year. Like this is roughly about 400 billion INR. So the current cold storage capacity is only able to cater about 13% of the country's total perishable. So this is as per the Ashocham report of 2013. Even in over the last 8 or 9 years, this figure has not gone beyond about 16 or something. So indeed, cold storage facilities are really a dire requirement. And this map really shows us this red areas where there is extreme shortage of these cold storage facilities. And then there are these green areas which have moderate shortage. And then there are these blue areas which have less shortage of such facilities. So Accordingly, what we can see is there is this farmers plight that the farmers are not really able to reap the benefits of their produce, and many a times we see that a lot of their products are rotting before reaching the market. And that's where there is one more question on asking your opinion. You can fill it later on. So over here, like the work done in our group, like in collaboration with one of the engineering departments here, uh, focuses on looking at biomass as a possible alternative source of fuel. And while we were showing this chart where I talked about all of these fossil fuels, like these fossil fuels have been formed in the Earth's crust over millions of years, right? And we have really taken about 2 centuries to exhaust all of them, or a major portion of them. So therefore, something which is perennially produced is going to be one of the possible options. And as we can say, biomass, particularly when we are talking about agricultural waste-based biomass. So that is something which is perennially produced. Every year we have this generated. And what we can see here is that this global annual energy potential of these biomass is about 120 exajoule. So 120 exajoule is about 3.8 terawatt year. And the annual energy potential for India is about 10 exajoule. So this is not very high, but it's still about, say, when we are talking about 1.2 terawatt year energy consumption, and something which is capable of serving about zero point 0.4 terawatt year, right? So this is 1/3 of our energy demands could be taken care by biomass. So if we suitably use biomass in conjunction with looking at sun, like tapping sunlight and tapping energy from, say, water streams, so hydroelectric power. So we should be able to like come above our dependence on fossil fuels. So therefore, like this biomass potential has to be explored further. So what has been a annual problem in our country is this field burning of crop residues. So about 100 to 140 megatons are burnt every year, and accordingly about 2.5 exajoules of energy is wasted. Like that much of energy potential is straight away wasted, and this can fulfill 10% of total primary energy consumption. So whatever is really wasted, that could really be utilized. However, there are important challenges here. So loss of soil fertility, particulate matter emission, winter smog, health issues, poor visibility, like these are kind of associated issues with this field burning of crop residues. So how can we develop a technology around biomass so that we are not really kind of facing these issues related to respiratory diseases or poor visibility or particulate matter emissions, but at the same time, we are able to satisfy this 10% of primary energy consumption requirement. So useful energy interventions are required. So perishables which are prone to damage, and there is a farm level wastage. How can we have off-grid solutions, like which are really exploiting this biomass for making these cold storages? So let us just try to look at some more data here. So there are these fruits and vegetables which are on-farm perishables, and the reason for deterioration is usually partly mechanical injury or parasitic diseases, and there are internal injuries related to physiological deterioration. So shelf life should be extended by storing goods at suitable climatic conditions. And when I say suitable climatic conditions, this means a controlled humidity and temperature environment. So this really brings us to this table, which is kind of reasonably well understood by now. So there are certain products which require very small temperatures, so low temperatures and reasonably high relative humidity for storage. So if for example, you store them at low humidity, they will lose their say internal constitution. So this potato or cabbage or cauliflower, they will no more be usable. They will no more be edible. Like if you are storing them in low humidity. So in addition to low temperature, this also requires high humidity. Similarly, like fruits like banana, guava, papaya, mango, they require a moderate temperature and high humidity. There are items like ginger, garlic, dry beans, or onions. They require moderate humidity and moderate temperatures. And then there are other items like chili, pepper, copra, green tea leaves, so tea processing, wood seasoning. They require high temperatures and low humidity conditions. So therefore, all this have to be kind of factored in when developing a technological intervention. So this field burning versus direct combustion, or direct combustion, like field burning or direct combustion is one of the big issues, right? So if we can avoid this field burning or direct combustion of these biomass residues, then it would be really very, very useful. So, and mind you, these numbers are really high. So the energy density of these biomasses like bagasse or rice husk or rice straw or coconut shell are quite high. And if we can evolve processes like biomass gasification, so basically what it involves is in partial oxygen presence, we take them through a thermochemical process, and uh, from this, useful gases like hydrogen or methane could be produced. So that really is the process of biomass gasification. And like if we can kind of use this biomass gasification to produce humidification, dehumidification, heating and cooling all at one go. So that was one of the important questions that we were trying to address. So let me come to the kind of. So before I come to this main issue, let me just kind of talk of this key research issues in the problem that we addressed. So here we wanted to design a versatile unit which could perform the task of heating, cooling, and a combination of heating and cooling, but at the same time also control humidity. So um, like all this together was a reasonably difficult task. So here I can sort of show you in a schematic the various parts of the system that we have developed. So there is a gasifier cum hot water generator. So over here, now if I tell you that gasification is a technique which could be applied to this biomass, and then we can make producer gas or synthetic gas, which is basically COH2 and methane, right? So some fraction of methane. Then you would say that this is a well-known technology, so why people have not really been using it? So it turned out direct burning versus gasification, like from thermodynamic calculations, um, like they don't appear to be different, right? So at the end of it, if you are conserving the entire energy content, they should not really be different quantities. But in practice, all the literature which has been existing in the area of biomass usage, they have conveyed that when you are using a process of biomass gasification versus directly burning the biomass, in the former, the efficiency is almost halved. So when we got into doing this problem, what we realized is this entire thermochemical process which takes place in the belly of the gasifier, there is lot of like waste heat which is generated. So basically the process is exothermic beyond a particular point, and lot of this heat is lost to the environment without being really tapped. So one of the technological interventions that we put in place was designing suitable heat exchangers which will preheat the water. So we will kind of preheat the water using the thermochemical exothermic heat of the gasification process, and then use a suitable burner to burn the synthetic gas which is produced, and then further heat the preheated water. So now you will ask me like, okay, we have generated hot water, so somehow we can address the heating part of the requirement. How do we really address the cooling part of the requirement? So here it turns out that there is an existing technology related to adsorption refrigeration systems. So one of the interesting adsorption, basically the adsorbate-adsorbent pair is calcium chloride and ammonia. So it turns out whenever ammonia is adsorbed on calcium chloride, the process is highly like, so basically what will happen is you need to supply lot of heat to desorb them. And when the adsorption happens, lot of heat is emitted into the environment. So this emission of heat and producing like providing heat, they can be put into a cycle which can provide a coefficient of performance, like leading to a refrigeration process. So this is something which is used in an adsorption based refrigeration system. And what we did was this hot water that we generated using biomass gasification, that was utilized to desorb the ammonia from the calcium chloride bed. So accordingly, like from biomass to biomass gasification to desorption, like we kind of also attained this cooling process. So now we have this heating and cooling both are in place. And then this hot water, like the steam which is generated, that could be used for humidifying, and the heat that we generate, that could be used for dehumidifying if we use suitable desiccant wheel. So accordingly, all four functionalities were brought into the system, and we developed a cold room facility which really runs on biomass. So we basically put in biomass, and then like it has a particular usage rate. So about 5 to 10 kilogram per hour, and then it can like keep a huge facility like for cold storage application. So that's how like this interesting technology was developed. And like this is a proof of principle technology that one can create different types of humidity and temperature controlled environments for processing and storage of different types of perishables. So now my question is, what is the other thing we generate the most perennially after biomass? So if we are saying biomass was a waste, right? So can somebody tell me which is the other waste which we generate the most? Somebody can unmute and convey which is the other waste that we generate the most. Yes, somebody is unmuting. Please go ahead.
So after biomass, the most wastage is our regular wastage from home actually.
From home. Okay. Okay. Somebody else. Can
It
you
is
introduce yourself, please? Can you introduce yourself, please?
I'm Dr. Srinivasan again.
Oh, Dr. Srinivasan. Yeah, and I will take some time to recognize voices. Yeah. So by the end of this session, we will know each other better. Yeah, thank you. So any other views? Okay, so Dr. Srinivasan has really hit the bullseye. So in fact, it is municipal solid waste, right, which is perennially generated. And so can we do MSW gasification for energy needs? So already there are research papers, there's significant amount of research done on it, but then there are certain limitations over here. So like MSW gasification for energy needs require usage of certain novel materials in the form of catalysts, right? And lot of research is desirable in this area. So therefore, need for novel materials for catalyzing the process of MSW gasification. So this is an open problem, right? Really challenging, interesting, open problem. And if we can really solve this problem, you will find biomass and agricultural waste and municipal solid waste together, like feeding into a major part of energy requirement that our society faces. Like not only that, it will also lead to community heating, uh, air conditioning, like so basically heating, ventilation, air conditioning requirements also. Because as soon as I demonstrated a system where we were talking about heating and cooling simultaneously, right? So it simply takes small innovations to convert it into an HVAC system. And you can talk about community heating, ventilation, air conditioning. So a lot of our dependence from grid power could be removed. In fact, we can really dream about a future where the houses of farmers, they have these kind of units, and they are using it also for climate control of their homes. So imagine having an air conditioned home all around the year, like heating during winters and cooling during summers, right? And all of us agree that the amount of energy that a country spends on heating, ventilation, and air conditioning, that also is an indicator of how developed that country is. So therefore, like this is going to be a technology which is really going to serve like us very nicely. And there is a need for novel materials for catalyzing the processes. So here I have taken a paper from Catalysts, like volume 8, uh, page number 113. You can go. This is not our paper. So where people are talking about how various types of intermediate products and products with high value for from market can also be produced as byproducts from municipal solid waste. So bioplastics, organic acids, furans, essential oils, apart from biodiesel, bioalcohol, syngas, biofuels, etc. So like this really is a rich resource which all of us should look into. And then there are interesting science problems or technology problems which needs to be addressed. So manufacturing each one of them in high yield will require useful interventions from nanotechnology in designing suitable catalysts, right? So that is a very important problem. And similarly, like improvising this entire variety of possible methods. So whether it is pyrolysis or gasification or combustion or incineration. So when we are saying these are different processes of burning depending on the amount of oxygen that we supply. So in the absence of oxygen, it is pyrolysis. With partial oxygen, it is gasification. In like the requisite amount of oxygen, it is combustion, and excess air, it is incineration. And they have their own different compositions, like the particularly in terms of ash, coke, slag, like there are various compositions which are arising. And you would have also heard about government's plan of mixing biomass with the coal in our thermal power plants. So that is another area which is very interesting to do future research. So here I am showing a like schematic from the same paper where they are talking about uh, like the waste collection from municipalities going into the waste bunker. So there is a rubbish pit from which the crane picks it up, sends it to a furnace. It eventually goes to boiler economizer. There is a scrubber. There are filters. There are catalytic denitrification equipment. And finally, clean air is emitted. And at each step, like there are technological interventions required. So if we design, so nobody else is going to design these technologies for us. If we want to kind of suitably address how to collect or capture hazardous waste materials, right? Or how to treat them, how to make suitable filters, how to make catalytic denitrification equipment. So at each of these steps, you can really find interesting science and technology problems, like which actually converts into some kind of a material science problem also, right? And leads to a development of a novel material. So again, I would like to alleviate this notion that novel material has to be compulsorily something which has very interesting constitutions. No, right. So you can have materials which are made in a particular manner following certain nano structuring protocols which make them novel. It could be a single element material, it could be a two element material, or it can even be a multi element material. So like these were the points which I wanted you to understand before we get into the talks by the other experts. And again, I will come back to this chain of different technologies which is invading our uh, like day-to-day work life, right? And you can see that each one is going to come up with huge energy demand, and therefore like lot of uh, interventions are required. So over last couple of years, we had some of the interesting publications and patents also coming out of this work. And at the end, I would like all of us to live with the thought that um, like thought of imagining a world where technology for sustainable energy can help us provide clean water, clean air, and adequate food for all. So developing affordable, sustainable energy solutions using novel materials will be at the heart of increasing access to pure air, clean water, and food security. So with this, I would stop this presentation and we'll go into the discussion mode. So let me see what really are. So I will check if there are some questions in the Q&A section. No, I don't see any right now. So how many of you have really filled the. So there was a Google form. So I would urge all of you to fill the Google form. So let me see. I have gotten only 3 responses till now. It's very much live. So let me see individuals. So we have Buddhadev, S. Verma, and Indumati. These are the only 3 people from whom we have gotten the filled Google Forms. I would expect everyone to fill it. Quickly submit it. And also I would request everyone to switch on their cameras so that we can interact now. So fourth one, somebody has, yeah, so S. Verma. Yeah, okay, so another person has submitted. Can people finish it? Like all those who are present in this session, can they quickly submit it?
Sir, I am Dr. Srinivas. Sir, please share the link again. Some of them have not received it.
Dr. Anil Singh, can you unmute yourself and introduce yourself? So we'll now have a short, quick knowing each other session. That would actually help us in continuing with the discussion further. Dr. Anil Singh, Dr. D. Satish Kumar, are you around? Dr. D. Satish Kumar. Dr. S.J. Pradibha. Dr. S.J. Pradibha. So I'm sorry, this is one of the pitfalls of online mode of discussion. We are really not sure if the session is logged in and the person is actually there. Dr. V. Nirmala. Right, let us start with someone. I think I saw a message from her. Dr. V. Nirmala, can you unmute yourself and introduce? Hello. Yeah, I would expect people to unmute themselves, so you can see that there is this toggle button, right? Mic. So you can click it to unmute yourself. Right, so I just muted and unmuted myself. So please unmute and speak up. It's okay to type in because we already have your data, some of your data, but not everyone knows you. So it is also a chance to know everyone and what people are working on so that we can have more fruitful discussions. And also for the offline session that would help make the groups properly. Yeah.
Hello.
Yeah, Dr. Palani. Yeah.
Yeah, shall I introduce, ma'am?
Yeah, sure. That's
Yeah.
fine. Please go ahead.
Yeah. Good evening. Good evening. This is Dr. R.
You can
Parani.
also switch on your camera, maybe switch on your camera if possible.
Okay.
Thank you so much. Yeah.
Yes. So myself, Dr. Parani. I'm working as an associate professor in the Department of Chemical Engineering in Sri Venkateswara College of Engineering, situated in Sribermuttur, Tamil Nadu. So my work experience here at the last 10 years I was working over there in the Sri Venkateswara College of Engineering, and total experience in teaching is 14 years, around 14 years. And my area of interest is carbon capture and material science and technology. And currently I'm working on carbon capture and nanosynthesis of materials. This was my
A number of thank you. A number of
Thank
speakers will be talking on relevant areas like what you are working on. Yes, thank you so much, Dr. Palani.
Thank you. Thank you.
Yeah, so we were going in sequence. So see. Dr. A. Vijay Lakshmi. Yeah, okay. Dr. Srinivasan has unmuted himself, looks like, yeah. We can also see you. Yeah, please go ahead. You have to unmute yourself.
So good afternoon, sir. I'm Dr. Srinivasan from RVS College of Engineering, Dindikal, Tamil Nadu. Presently, I am professor and head of the department for in that college of mechanical engineering. And my areas of interest are materials, particularly because I'm interested in metallurgy part. And moreover, I'm interested in the sustainable development, particularly with the energy as well as the waste recoveries like that. So that is where developing energy from the waste. Thank you, sir.
Glad to know that we need to have such a kind of set of people within the country to push this area further, right? We need to cross the threshold mass, right? Because other areas are more appealing immediately, and it like this is one of the area which requires a lot more people to come into. Yeah, thank you, Dr. Srinivasan. Dr. Binu S.
Yes, sir. Good evening. Good afternoon.
Yes.
I am Dr. Binu S.
Yes.
Working as an assistant professor in the Department of Physics, College of Engineering, Trivandrum. The areas of research are design and fabrication of fiber optic sensors. Thank you, sir.
Okay, thank you. Thank you so much. Yeah, somebody else?
Good evening, sir.
Yes.
I am Dr. Ilayarasan from Eastern Engineering College, Chennai.
You can also kind of switch on your camera. Thank you. Yeah, please go ahead.
Good evening, sir. Sorry, is my voice clear?
Yes, your voice is clear. Please go ahead.
Yes, I am Dr. Ilayarasan from Eastern Engineering College, Chennai. My major stream is ME and PhD in Manufacturing Engineering. Currently, I am working on research on surface engineering, sir, surface coating.
Right, right.
Thank you, sir.
Okay, thank you, thank you, thank you. So we are getting to know each other. Yeah, thank you so much. So Dr. A. Gangadhar. Okay. Dr. Shalini Jaiswal. Dr. Buddhadev Pradhan.
Yeah, good evening, sir. Am I audible?
Yes, you are
Hello.
audible.
Okay.
Yes, you
Good
are
evening.
audible. You can also switch on your camera. Yeah.
Actually, sir, I use my desktop. There's no any
Oh, I see, I
camera.
see. Please go ahead. Please go ahead.
Yeah,
Please
yeah.
go ahead.
So I am Dr. Buddhadev Pradhan. I am actually from the Kolkata, West Bengal. I actually assistant professor in Techno India University, Kolkata. And my relevant field for this research in the MEMS technology based on the different types of the electronics component in the high frequency applications in the satellite and other domains also. So we may try to implement some of the sensor based on the different types of the materials using the different of the IoT and 5G systems also.
Right.
Okay, thank you.
Okay. Okay, thank you. We'll have some talks in offline mode related to your relevant area.
Okay,
Yeah.
okay, sir. Thank
Okay.
you.
Okay.
Yeah.
Okay. Fine. Okay, so we had Dr. A. Gangadhar, Dr. Shalini Jaiswal. Any of you around? Dr. Indumati. Dr. Birla. Dr. Pratap Singh Birla. Dr. Rajkumar. Dr. Shubham Kumar. Dr. Yogesh Deshpande. Okay, some of them are on hold. I think Pratap Singh Bidlaji and Yogesh Deshpande, they are on hold. Seems they're attending from mobile and so anyone else would like to introduce themselves? We had very few introductions right now. And I also did not find much questions in the Q&A section. So as I already kind of motivated that today's session was primarily to kind of push forward this need for thinking about novel materials for sustainable development. and it is applicable to all domains which were marked there, right from IoT to nanotechnology. So, and various interventions of it for clean water, clean energy, clean environment, remaining connected, low power end applications. So yeah, so many different areas will require novel materials from a sustainable perspective, because as soon as a volume of trade is going to increase in a particular domain, say when there were only limited number of displays required, then using indium was not an issue. But now when we are requiring displays in a much larger number, then indium shortage is really going to pinch us today or tomorrow, so very soon. So in a similar manner, in various domains, we will be having issues cropping up. One of the reasons for success of silicon technology or silicon-based technology has been the abundant availability of silicon. Okay, are there some questions? Let me quickly look at the Google Sheet again if there are. So there are 12 responses. Okay. I will go through these responses in more detail and kind of send feedback. Let us start with some of them here. So give 3 examples where materials have made our lives more comfortable. So mobile phone communication devices and different types of sensors and applications. So and give 2 reasons why indiscriminate use of material is not sustainable. Cost effective and more demand. Okay. So definitely indiscriminate use will actually be limited by availability of the ingredient materials. So that's one issue. So shortages of materials. Say I was just giving this example of indium shortage. The other could be environmental impact. So indiscriminate use would involve indiscriminate production of these materials, and at times the processes may not be environment friendly, or the total cost, as we know, like not only the cost in procuring these materials, but also the cost to environment and the ecosystem taken together may be very high. So explain in your word what you understand by sustainable. Okay, sustainable development is an organizing principle for meeting human development goals in different domains. But when we say sustainable, we have to also keep in mind that while we like use the benefits of technology, it should also pave way for future generations to be able to use the same technology. So we should not exhaust the resources. So that is where this notion of sustainability comes in. So how can water security be ensured? Purity and use different materials. So definitely, like so we have a large coastline. So if there are technologies developed for desalination, which are kind of convenient or less energy intensive, so over there also a lot of novel materials would be required, right? They have their own role to play. So that would be an area where we can really address part of the water security issue. Also, like purification of water, purification of contaminated water. Like if we can achieve that in a cost effective manner, and say also focusing on energy going into it. So that would be another kind of way. And how can food security be ensured? So prevent the food wastage, maybe what you're going to say, using different material packages. Okay. So fine. So that is one option. But then food security, definitely there is this associated point of having a storage chain, right? So cold storage chain or food processing chain, that is kind of relevant. Somebody else has mentioned for living in world, food is one of the major requirement. As per my opinion, we should ensure zero wastage and feeding those who are unable to get the food. Thank you. By utilizing the water resources optimally, harvesting the rain, fog, and dew for accomplishing water needs. So nice answers. So meeting present need without impacting future resources. So that is also good. So as we can see, IoT, virtual reality, augmented reality, they can have a sustainable future if and only if we are kind of going off grid for them, for their usage. So say if, like take a very simple example of an IoT device, which is say continuously monitoring temperature of a particular region. Now, if this temperature sensor that requires electricity power, like so these sensors have very small energy requirements, say wattage requirements. However, if we are using it from grid, there is going to be a down conversion. So there would be a transformer based AC to DC conversion, and then at a very low wattage rating, right, we are going to use it. But this process of down conversion, lot of electricity is converted to waste heat, and that is not really usable. So therefore, like direct usage on of grid power is something that we have to avoid. So alternate sources of energy harvesting have to be developed. So only then this IoT will see a bright future. IoT devices. Give two reasons why discriminate use of material is not sustainable. For sustainable development, a material should be such that it get disposed to. If not, then doesn't support. So okay, thank you. So here like there is this buzzword associated with this idea known as circular economies. So material should be recycled, right, to the extent possible. So that is one of the important um, things. So you can also see there. So similar answers here for water security, increasing forest cover is key. Yeah, so something which is common sense is less common use of yeah, so we need to really have more tree plantation and other things definitely. The largest demand on water is from agriculture. Judicious use of water for agriculture is key for managing the water challenge. Micro irrigation is crucial. Thank you. Sustainable development is development that meets the need of the present without compromising. Yeah, so this is from the quote. Thank you. Yeah, fine. So about 13 people have answered. So that is okay. At the moment, I can see. I will be closing this form soon, so maybe in another 15 minutes, 10-15 minutes, you should try to submit it. By 5:15, I would be closing these forms. So if there are no questions, no further questions, we can close today's session. Tomorrow's session would be as per the schedule, so that would start at 7 p.m. Right, so Dr. Srinivasan, you have raised your hand, please go ahead. There's a question, it seems.
Yeah, it's a question, sir. I already typed the question in the chat box.
Okay,
Anyhow.
let me, so yeah, let us see that. Just hold on. Okay, so when you are saying briquetting, right? So even for biomass gasification, we are going through this briquetting stage. So there is already a, okay, so Anita Gupta ji is saying she did not receive. You can simply look up in the chain of discussion. Anyway, I'm trying to post it again. So Dr. Gupta, you can see in the chat messages, You can check previous messages and you will
sir,
find
I didn't
this.
get the link from the chats. Sorry
Oh, you
for
did not get the
interruption, sir.
link? Can somebody just repost it? Can somebody help me by reposting it? Because I have already
Sure, I
posted
can
it.
repost.
Yeah, please repost it. Thank you.
Thank you,
I'm
sir.
sharing just
Okay, I will do.
possible.
Just I am posting it again.
Okay.
Okay, I have posted it
Yes.
again. That's fine.
Received.
What
Thank
we
you,
can
sir.
do is, when we have such issues, right, among participants itself, it's no harm by reposting the same link. That would help. Yeah. So we had a question related to briquetting. So it turns out even the conventional process of biomass gasification that we use, we are using briquetting. Okay, so briquetting really ensures that the process becomes more efficient. So the energy density per is enhanced in the process of briquetting. So specific energy density is enhanced. So however, what you are talking about is for rural energy demand, can we directly use briquetting? So it turns out this is again going to fuel this direct burning. So direct burning has associated issue of particulate matter. And accordingly, there could be other associated ecological changes that one can observe, like say as if we uh, increase our dependence on briquette burning, right? So that would lead to more smog, more maybe uh, so basically villages will also become, or rural areas will also have an environment very similar to cities in terms of smog and other things. So that is where this gasification provides a clean alternative. Of course, some of the other alternatives that we will listen about across these talks over next 1 week also involve things like making fuel cell, or making, say, photocatalytic decomposition of water into a clean fuel as hydrogen. So over there, the material intervention is from the perspective of developing suitable photocatalysts. So that those are really points where very interesting research areas could be defined and problems could be picked up. So I hope I have partly answered your question, Dr. Srinivasan. Yeah. So let me just check if there are more questions. No, they were primarily request for links and introductions. Yeah. Okay, thank you so much. So see you everyone tomorrow at 7 p.m. We'll have Dr. Ujjal Gautam from ISR Mohali as the speaker for tomorrow. Yeah. Thank you. We'll close this session. Thank you so much for your presence. Maybe you can leave the meeting. I would be the last one to leave. Yeah. If there is any question, I would still take. There are some people who wait. Like okay, so we are closing this session. If there are any questions, you can ask. Otherwise, we'll close this session. It seems some of you joined late.